Usually when we look at the history of a government agency, you sort of expect this very dry, boring bureaucracy.
Right, just endless organizational charts and paperwork.
Exactly. You look at the funding allocations, the departments, and you expect this very steady, predictable march.
You assume it's an entity that just finds a niche and stays strictly within its lane.
Yeah, never really rocking the boat. But then you step into the world of the National Aeronautics and Space Administration, NASA.
And suddenly that predictable org chart is just strapped to a rocket engine.
It really is. What you find in the source material isn't a stagnant bureaucracy at all. It's a story of absolute sheer panic.
Oh, for sure. Panic, followed by these massive engineering triumphs.
Right, and then a bizarre detour into essentially venture capitalism.
And now, literal planetary defense.
Welcome to the deep dive into the source material. Today, our mission is to unpack this massive encyclopedic history of NASA.
We're tracing the journey from its Cold War origins all the way to its current status right now in April 2026.
And I have to say, for you listening right now, this really could not be more urgent. I mean, just this month, Artemis II put a crew into a lunar flyby.
Which is an incredible milestone.
Huge. And we have a brand new NASA administrator, Jared Isaacman. Plus, there is this literal fast-tracked government mandate to put a nuclear fission reactor on the moon.
Yeah, to secure what they're actually calling keep-out zones.
Which is wild. So that phrase alone should tell you we aren't just looking at history for the sake of history today.
No, we are looking at the blueprint for humanity's industrial and geopolitical future in the cosmos.
Okay, so let's unpack this, because I was actually shocked to find out that the spark that created NASA didn't start with space at all.
No, it didn't even start with rockets.
It started with airplanes, and honestly, a deeply bruised national ego.
Right. The origins actually trace back to 1915 to an organization called NACLA.
That's the National Advisory Committee for Aeronautics, right?
Exactly. And the reason it was created is completely ironic, especially given American history.
Because the U.S. invented the airplane. The Wright brothers in 1903.
Right. But by 1914, just 11 years later, World War I begins, and the U.S. government realizes something painfully clear.
They invented this machine, but Europe just immediately weaponized it.
Yes, and rapidly advanced the technology. The Europeans were building these advanced fighter planes and bombers.
While the Americans were essentially still tinkering in bicycle shops.
They had fallen dangerously behind in their own invention.
So it's like, I don't know, it's like inventing the internet, but then waking up a decade later and realizing another country has built the entire modern tech economy.
And you're still using dial-up.
Exactly. So Congress panics. They create the aviation section of the Signal Corps in 1914, and then they establish NACA in 1915 to just claw back that lead.
And for 40 years, NACA does exactly that. They become the premier aeronautical research lab.
They test wing designs in these massive wind tunnels. They help break the sound barrier with the Bell X-1.
They were true aviation pioneers. But then, the board gets flipped entirely.
Because the Soviet Union launches Sputnik 1, October 1957.
The starting gun of the space age.
And I want to pause here, because the level of panic this induced, it's really hard to overstate.
It was unprecedented.
It wasn't just like, oh, darn, they beat us to space. It was this terrifying realization that if the Soviets could put a metal sphere into orbit...
They could put a nuclear warhead on that exact same rocket.
Right. And hit anywhere in the United States, and there was absolutely nothing the U.S. could do to stop it.
Precisely. To the U.S. government, Sputnik wasn't a scientific triumph. It was a demonstration of an intercontinental ballistic missile capability.
No, the U.S. wasn't sitting completely idle before this.
No, NASA actually had a rocketry program. But the initial responsibility for the first American satellite was given to the Navy.
Project Vanguard, which was an absolute disaster.
A very public disaster. The Vanguard launch in December 1957 literally lost the thrust of a feet off the pad, fell back, and exploded.
On national television, the press dubbed it Kaputnik or Flopnik.
Yeah, it was a staggering humiliation on the global stage.
So that failure forces the hand of the Eisenhower administration.
They had to turn to the Army Ballistic Missile Agency, led by Wernher von Braun.
And they successfully launch America's first satellite, Explorer 1, just a couple of months later.
Right, in early 1958. But this internal competition between the Navy, the Army, and the Air Force, it was incredibly inefficient.
So Eisenhower makes this massive, sweeping decision to consolidate everything, but he does something really specific that defines NASA to this day.
He splits military and civil spaceflight.
Which is wild to me, because if rockets are essentially ICBMs, why create a civilian agency at all?
It was a geopolitical masterstroke, honestly.
How so?
By taking the military's advanced rocketry, packaging it with NACA's scientific research labs, and slapping a civilian label on it, the U.S. could present a face of peaceful exploration to the world.
Ah, so it's a PR move.
A very strategic one. It allowed the U.S. to aggressively develop heavy-lift rocket technology without appearing overtly aggressive during the Cold War.
So the Air Force handles the covert military stuff, like spy satellites.
And NASA becomes the public, smiling face of American ingenuity.
So October 1st, 1958, NASA officially opens its doors. They absorb NACA's employees, the Jet Propulsion Lab, von Braun's team.
It's basically a Frankenstein organization born entirely out of Cold War anxiety.
Right. But I have to ask, did this intense pressure actually save the agency? Because mashing together the Army, the Navy, and a bunch of scientists sounds like a recipe for endless committee meetings.
Well, the existential threat of Soviet dominance eradicated all that usual bureaucratic friction.
Yeah, there was just no time for it.
Exactly. President Eisenhower mandated that the first astronauts, the Mercury 7, had to be active-duty military test pilots.
Which makes sense. You need people used to extreme risk.
Highly experimental, dangerous aircraft. They were flying by the seat of their pants.
I mean that literally. Look at John Glenn's orbital flight in Friendship 7. We think of spacecraft today as these highly automated vehicles.
But Glenn had to manually fly his capsule using hand controllers.
Right, for parts of his final orbits because an automatic thruster malfunctioned.
If he hadn't physically wrestled that capsule into the correct orientation for re-entry, he would have burned up.
The technology was so crude by today's standards.
He was essentially a tin can strapped to a modified ballistic missile.
But Project Mercury proved humans could survive space, right?
Yes, that was the primary objective. Survive the G-forces, endure microgravity, and safely return.
So once they knew the human machine could survive, they moved to Project Gemini.
Gemini was the critical bridge to figure out the operational mechanics.
Because getting to the moon, which Kennedy had mandated, requires a whole different skill set.
Exactly. Gemini allowed them to fly 2 astronauts at a time and keep them in orbit for up to 2 weeks.
To simulate the time it would take to go to the moon and back.
Right. But more importantly, Gemini is where NASA learned how to perform orbital rendezvous and docking.
Which is taking 2 vehicles moving at 17,000 miles per hour and gently connecting them in a vacuum.
It's incredibly difficult. They also pioneered spacewalks during Gemini.
Because you can't go to the moon if you don't know how to step outside the vehicle.
Exactly. And mastering docking was vital because of how the Apollo missions actually functioned.
Yeah, I always assumed they just built one giant rocket, shot it straight to the moon, landed the whole thing, and flew it back.
You're referring to direct descent, which was considered initially.
But they didn't do that.
No, the physics of direct descent are a nightmare. To carry enough fuel to land an entire massive rocket on the moon and take off again, you'd need a launch vehicle the size of a skyscraper.
Like, practically impossible to build in the 1960s?
Right. So instead, they used Lunar Orbit Rendezvous, or LOR.
How does that work?
With LOR, you launch a modular system, a command module, and a smaller lunar module go to lunar orbit together.
And only the small, lightweight lunar module goes down to the surface.
Exactly. It requires vastly less fuel to take off from the moon to get back to orbit, where it docks with the command module for the trip home.
But that meant they absolutely had to master docking in space.
Which is why Gemini was a prerequisite for Apollo.
Man, the scale of Apollo just breaks my brain. The estimates say that at its height, like 5% of all Americans were working on some aspect of it.
The budget was effectively a blank check.
But even with unlimited money, the engineering hurdles were terrifying. Like the F1 engines on the Saturn V rocket.
The F1 is still the most powerful, single-nozzle, liquid-fueled rocket engine ever flown.
And I was reading they had this massive problem with combustion instability.
Yeah, when you're pumping thousands of gallons of fuel into a chamber every second, the combustion isn't smooth. It creates acoustic pressure waves.
And in early testing, those waves would resonate and literally tear the engine to shreds, right?
In fractions of a second.
How do you even fix that when you are trying to beat the Soviets to the moon? You can't just run computer simulations in the 60s.
No, they fixed it through brutal empirical testing. They built physical baffles inside the injector plate to break up the waves.
And to test it, they literally detonated small explosive charges inside the engine while it was firing at full thrust.
Exactly. To see if the engine could damp out the resulting pressure spike, it was engineering by brute force.
And it worked. Apollo 8 goes to the moon in 1968, takes the famous Earthrise photo.
And then Apollo 11 lands Neil Armstrong and Buzz Aldrin in 1969.
They win the sprint. The existential threat is neutralized. But this brings us to a massive structural problem, doesn't it?
It does. Apollo was a sprint, and NASA was an agency built for a sprint.
So once you cross the finish line, how do you convince Congress to keep funding a marathon?
That is the central crisis that shaped the next 4 decades of American spaceflight. The political mandate for a blank check space agency just vanished.
So Apollo gets cut short, ending with Apollo 17 in 1972.
And NASA has to pivot. They have to justify their existence through sustained economical access to space.
Which brings us to the 1970s and 80s, the era of reusability.
They started by just recycling leftover Apollo hardware for Skylab in 1973.
Their first space station. But the real symbol of this transition is the space shuttle.
The machine that defined NASA for a generation.
Looking back at the original pitch for the shuttle, it sounds like absolute science fiction.
NASA sold it to Congress as a space delivery truck.
Right, because throwing away a multi-million-dollar rocket every time is unsustainable.
So the shuttle was designed as a reusable spaceplane. Launch like a rocket, deploy satellites, and glide back to a runway.
And they promised it would fly dozens of times a year, right? Dramatically lowering costs.
But the reality was so different.
Yeah, I look at the shuttle and I don't see a reliable delivery truck. I see a hyper-advanced sports car that you have to completely disassemble and rebuild after every grocery run.
It came down to the extreme violence of spaceflight and the fragility of the tech.
Like the thermal protection system, the tiles.
To survive re-entry, the underside was covered in thousands of unique silica tiles. They were incredible insulators, but essentially made of aerated glass.
You could crush them with your bare hands, right?
Yes, and they were glued to the airframe. After every flight, hundreds of them had to be individually inspected, repaired, or replaced.
And the main engines were just as demanding.
Engineering marvels, but they operated at such extreme pressures, they had to be removed, torn down, and inspected for microscopic fractures between flights.
So the labor required was astronomical.
It never achieved the rapid turnaround, so it never achieved the cost savings. It was a strategic trap.
It kept NASA geographically locked in low Earth orbit for 30 years.
Just spending most of its budget maintaining the vehicle.
And we really can't ignore the human cost of that fragility. Challenger in 1986, Columbia in 2003.
When you have a vehicle wrapped in fragile glass tiles launching alongside external tanks covered in foam.
A piece of foam breaks off during launch, strikes the wing like it did with Columbia, and the vehicle is doomed upon re-entry.
The loss of Columbia was the final breaking point. The Bush administration mandated the shuttle's retirement as soon as it finished building the International Space Station.
Now, the ISS is fascinating because here we see geopolitics overriding pure science again.
Absolutely. Back in the 80s, NASA wanted to build Space Station Freedom, but it was too expensive.
Then the Soviet Union collapses. Suddenly you have all these highly trained Russian rocket engineers sitting around with no funding.
And the Clinton administration pushed to merge the American and Russian designs.
Primarily to keep those Russian engineers employed, right?
It was a non-proliferation strategy masquerading as a scientific partnership.
So they didn't want Soviet missile experts selling their expertise to rogue states.
By bringing Russia into the ISS, the U.S. kept their aerospace sector tethered to a peaceful international project.
Which is brilliant diplomacy. But it set up a terrifying vulnerability.
Yes. In 2011, NASA retires the space shuttle.
The ISS is up there, flying at 17,500 miles an hour, and the United States has absolutely zero capability to launch a human being to it.
For nearly a decade, NASA had to buy seats on Russian Soyuz rockets to visit their own space station.
It's an incredible strategic failure.
It forced a total operational paradigm shift. NASA realized they could not afford to build another government-owned vehicle for low Earth orbit.
The development cycles were too long, and the cost-plus contracting model was bleeding them dry.
Yes, understanding the contracting model is crucial here.
Can you explain cost-plus? Because it sounds completely backwards.
In traditional aerospace, NASA designs the vehicle down to the bolt. They hire a contractor like Boeing to build it.
Okay.
And NASA agrees to pay the contractor for every single cost incurred during development, plus a guaranteed percentage of profit on top.
Wait, so if the contractor makes mistakes, and the project takes an extra 5 years and $1 billion, they actually make more profit.
Exactly. There is zero financial incentive for speed. The system financially penalizes efficiency.
So to escape this post-shuttle, NASA initiated the Commercial Crew Program.
And they shifted to fixed-price contracts.
This is the commercial revolution. NASA essentially becomes a venture capital firm.
They stop trying to build the buses. They just tell the private sector, we need a ride to the ISS. We'll give you seed money.
You design it, you own it, and if it's safe, we'll buy a ticket.
Under fixed price, if a company runs over budget, the company eats the loss, not the taxpayer.
It forces rapid iteration.
Yeah.
And the contrast in how companies handled this is staggering.
You have SpaceX, an upstart leaning into this agile model, blowing up prototypes, iterating.
Right, and they succeed wildly. Crew Dragon has been flying since 2020.
But then you have Boeing, the titan of legacy aerospace.
And their Starliner capsule is a textbook example of a culture clash.
They attempted to execute a fixed-price contract using a legacy cost-plus bureaucratic culture,
Relying on paper analysis instead of physical hardware testing.
resulting in years of delays, software anomalies, and a near-catastrophic first crewed flight.
Yeah, let's talk about that. We're sitting here in 2026. Just over a year ago, Boeing left 2 astronauts stranded on the ISS for 6 months.
Because the Starliner thrusters were failing, and they couldn't trust it to undock safely.
NASA had to officially freeze Boeing's contract in October 2024. Does that prove the commercial model is too risky?
I'd argue it proves the exact opposite. Because NASA funded multiple providers ensuring SpaceX was also developing a vehicle, the U.S. still had access to space.
Right. If they'd only contracted Boeing under the old model, the whole program would be grounded today.
The commercial model provided the redundancy that saved the program.
And the goal of outsourcing low Earth orbit was always to free up NASA's budget for the deep space stuff. Artemis.
The return to the moon. But deep space logistics are exponentially harder.
Yeah, looking at the recent timeline, they're struggling there too. Artemis II just did the lunar flyby this month, which is amazing.
But the plans for actually landing are changing rapidly.
Just 2 months ago, in February 2026, NASA radically changed the Artemis III mission.
It was supposed to be the first landing. Now it's just going to be a docking test in low Earth orbit.
Between the Orion capsule and SpaceX's Starship, the actual landing is pushed to Artemis IV in 2028.
And in March 2026, they completely canceled the Lunar Gateway space station.
Why the sudden massive pivot?
Administrator Jared Isaacman brought a very commercial perspective to the agency.
Meaning he cut the fat.
Essentially, the Lunar Gateway, a staging space station orbiting the moon, requires immense energy to maneuver in and out of its orbit.
So it was creating a bottleneck.
An unnecessary, highly complex bottleneck. By canceling it, they're stripping away bloated legacy requirements to focus directly on a surface presence.
Which is pragmatic, but it really highlights how fragile human spaceflight is. We're so constrained by our need for food, water, radiation shielding.
Which leads to a fascinating realization about the other half of NASA.
Right. While the human side struggles with timelines, the robotic exploration programs have been quietly dominating the solar system for decades.
From a pure data-gathering perspective, robotic explorers are the true vanguard. They don't need life support.
They don't need a return vehicle, and they don't complain about a 6-month commute to Mars.
And they organize these missions very differently. Competitive tiers to balance risk and budget.
Like the Explorer program at the smaller end.
Capped around $150 million. Highly focused single-instrument missions. Then you step up to the Discovery program,
which is capped around $500 million.
This is where scientists submit competitive proposals to answer specific questions. It's how we got missions to Venus and asteroids.
Like a scientific Hunger Games, NASA picks the best pitch.
It drives massive innovation. Then there's New Frontiers, capped around $1 billion for larger missions like New Horizons to Pluto.
And finally, the large strategic missions, the flagships.
Multi-billion-dollar behemoths tackling the highest priority science goals.
And historically, the highest priority is Mars. The Mariner flybys, the Viking landers, the rovers. But landing a massive rover is insane.
The Martian atmosphere is thick enough to burn you up, but too thin to slow you down with just a parachute.
So how did they land Curiosity and Perseverance? They weigh like a ton each.
They use the sky crane maneuver, often called the 7 minutes of terror.
Because with the smaller 90s rovers, they just wrap them in airbags and let them bounce, right?
Right, drop and bounce. But a 1-ton rover would shatter the airbags and destroy itself.
So the bouncing is out, and they come up with this idea that literally sounds like a Wile E. Coyote cartoon.
The spacecraft enters the atmosphere at hypersonic speeds. It deploys a massive parachute, but it's still falling too fast.
Okay.
So it drops the parachute, and a descent stage, essentially a jetpack, ignites retro rockets to hover a few dozen feet above the surface.
And while it's hovering, it lowers the rover down on a tether?
Yes, it lowers the rover on a bridle. The moment the wheels touch the dirt and detect the weight transfer, pyrotechnic charges sever the cables,
Wow.
and the descent stage throttles up and flies away to crash land a safe distance away.
Leaving the rover perfectly placed. And the craziest part is this is completely autonomous because of the light delay between Earth and Mars.
By the time NASA gets the signal that it entered the atmosphere, the rover has already been on the surface, dead or alive, for several minutes.
It's a masterpiece of engineering, and they're finding crucial data. Curiosity discovered that radiation levels on Mars are comparable to what astronauts experience on the ISS.
Which is a vital detail. Radiation is the silent killer of deep space exploration.
Because if the radiation was significantly higher, long-term human habitation would be almost impossible without living deep underground.
Exactly. Knowing it's comparable to the ISS means we already have a baseline understanding of how to manage that exposure.
But Mars isn't the only target. If we're looking for life, the outer planets are stealing the spotlight.
The astrobiology paradigm has completely shifted. We used to think life required the Goldilocks zone where liquid water exists on the surface.
But robotic probes changed that. Galileo at Jupiter, Cassini at Saturn.
They revealed that moons like Europa and Enceladus have massive global oceans of liquid water trapped beneath miles of solid ice.
But how is water liquid that far from the sun? It should be frozen solid.
Tidal heating. As these moons orbit massive gas giants, the immense gravity physically stretches and squeezes the moons,
Ah, so the friction generates internal heat.
keeping the oceans liquid and potentially driving hydrothermal vents at the ocean floor, very similar to where life thrives in Earth's deep oceans.
Which is why NASA is sending the Europa Clipper mission right now to fly through the plumes of water erupting from the ice.
And we also have to mention the space telescopes, another area where robotics redefine our understanding of reality.
Like the Hubble Space Telescope. Though the story of Hubble is almost a tragedy at first.
Launched in 1990, cost billions, and when they turned it on, the pictures were blurry.
Because of spherical aberration, right. The primary mirror was polished to the wrong shape by a fraction of a hair's width.
The ultimate measure twice, cut once failure.
But because it was in low Earth orbit, they sent shuttle astronauts up to physically install corrective optics. They literally gave it glasses.
But we can't do that with its successor, the James Webb Space Telescope.
No, JWST is parked a million miles away at a Lagrange point. What exactly is that?
A Lagrange point is a region where the gravitational pull of the Earth and the Sun equals the centripetal force required for an object to move with them.
So it's a stable parking spot in space.
The L2 point is a million miles behind the Earth, looking away from the Sun.
Why does it need to be there?
Because JWST observes in the infrared spectrum, which is essentially heat. If it was in low Earth orbit, the heat from the Earth and Sun would blind its instruments.
So at L2, it deploys a massive sun shield to keep its instruments near absolute zero.
But being a million miles away means it's entirely beyond human servicing. The deployment sequence had 344 single points of failure.
Unfolding a telescope the size of a tennis court in the dark. And it worked flawlessly.
Capturing the formation of the first galaxies.
It's stunning. But what I find really compelling is that while NASA spends billions looking outward, they're simultaneously spending massive resources looking back at Earth.
Earth science and planetary defense.
Though Earth science causes a lot of political friction.
Yes. NASA operates fleets of satellites. Landsat, Aqua, Aura tracking weather, and climate change.
And from an objective standpoint, NASA's published data concurs with the global scientific consensus that the climate is warming.
However, because climate change is so politicized terrestrially, there are constant debates over NASA's budget.
Some political factions argue NASA should transfer Earth observation to NOAA and focus exclusively on deep space.
Well, scientists point out that Earth is technically a planet, and studying it has been part of the mandate since 1958.
It's a tug of war. But there is zero debate about planetary defense. I mean, nobody is pro-asteroid.
Indeed. NASA formally established the Planetary Defense Coordination Office in 2016.
The mandate is to find 90% of all near-Earth objects larger than 140 meters.
An object that size wouldn't be a global extinction event, but it would wipe out a metropolitan area or cause devastating tsunamis.
And finding them is hard. Dark rocks against a dark background. So they're launching NEO Surveyor in 2026, an infrared telescope.
Because a rock absorbs heat from the sun and glows in infrared.
But what do we do if we find one heading right for us? We aren't sending oil drillers with nukes like in the movies.
The physics of that are highly problematic. You just turn one large rock into multiple highly radioactive smaller rocks hitting the Earth.
So the preferred method is a kinetic impactor,
which NASA proved works with the DART mission in 2022.
They literally played cosmic billiards.
That's exactly it. They slammed a spacecraft into a small asteroid named Dimorphos at roughly 14,000 miles per hour.
They didn't blow it up, they just transferred kinetic energy to change its momentum.
The goal was to alter its orbital period by 73 seconds. They altered it by 32 minutes.
A massive success. It proves that if we have enough warning time, we only need to nudge an asteroid slightly.
A tiny fraction of a degree change millions of miles away means it will completely miss the Earth.
We are the first species capable of altering the solar system's mechanics to prevent our own extinction.
It's a profound milestone.
But the tech we're developing also sets the stage for Space Race 2.0. And this gets intense. We're talking about big actual nuclear fission reactors in space.
Two parallel tracks of nuclear technology. First is propulsion. The Duraco program, partnering with DARPA, is building a nuclear thermal rocket for testing in 2027.
How does that compare to a chemical rocket?
Chemical rockets mix fuel and an oxidizer, they ignite, and the explosive exhaust pushes you forward. Powerful, but inefficient.
Okay, and a nuclear rocket.
You have a small fission reactor that generates immense heat. You pump liquid hydrogen directly through the core. It expands violently and shoots out the nozzle,
Producing thrust at roughly twice the efficiency of the best chemical rockets.
which is the enabling tech to cut the travel time to Mars from 7 months down to maybe 3 or 4.
Solving the radiation exposure problem because you spend less time in deep space.
But propulsion is only one half. The other track is surface power.
This is that July 2025 directive from the government we mentioned. A mandate to fast-track a 100-kilowatt nuclear reactor on the moon.
Yes. And the justification wasn't purely scientific. It was prompted by intelligence suggesting China and Russia might deploy a joint lunar reactor by the mid-2030s.
So the government warned that whoever establishes power first will dictate lunar operations and create keep-out zones.
Effectively denying the U.S. access to strategic areas like the water ice deposits at the lunar South Pole.
So power is literally currency. With a 100-kilowatt reactor, you have power to run life support through the freezing 2-week-long lunar night.
You can mine the regolith, extract water, split it into hydrogen and oxygen for rocket fuel.
You essentially have a permanent gas station and fortress on the moon.
By framing it around preventing adversaries from establishing keep-out zones, NASA is explicitly blending its civil exploration mandate with national security.
We've moved from exploration into the geopolitics of permanent occupation. It's deeply unsettling.
Exporting terrestrial border disputes to a celestial body.
And what worries me is that we are building these high-tech geopolitical chess pieces, but space exploration is still incredibly vulnerable to just mundane human screw-ups.
Like the Mars Climate Orbiter in 1999.
Yes. The ultimate, I thought you were bringing the map moment. Hundreds of millions of dollars on a probe to study the Martian atmosphere.
It gets to Mars, fires its engines to enter orbit, goes way too low, and burns up.
Because the team at Lockheed Martin that built the thrusters programmed their software using imperial units, pound seconds.
And the navigation team at NASA's Jet Propulsion Lab was using metric units, Newton seconds.
A catastrophic failure of systems integration. The software was just feeding raw numbers without converting them.
It highlights that in spaceflight, the simplest assumptions are often the deadliest.
Which is why standardization is so critical. And speaking of rigorous standards, NASA recently decided to apply its scientific rigor to unidentified aerial phenomena, or UAPs.
Yes, in 2022, NASA formed an independent study team to investigate UAPs.
To be clear, they aren't searching for little green men.
No. The mandate was to bring an objective framework to sightings and sensor anomalies reported by military pilots.
Because if a pilot sees something defying aerodynamics in restricted airspace, it's either a sensor glitch, a classified drone from a foreign adversary, or an unknown atmospheric phenomenon.
All three are major safety hazards requiring investigation.
By involving themselves, NASA signaled a willingness to engage with unexplained phenomena using their transparent analytical frameworks.
Standardizing how we observe anomalies.
And standardization, rules of the road, is really the final piece of the puzzle here. NASA requires a massive global web of partnerships now.
The International Space Station is the prime example. It integrates the European Space Agency, Japan's JAXA Canada,
The ESA is literally building the service module for the Orion spacecraft.
keeping American astronauts alive on their way to the moon.
But the rules are changing as we go back to the moon. We're laying claim to territory and resources, hence the Artemis Accords.
Arguably the most significant piece of space diplomacy since the 1967 Outer Space Treaty. Over 24 nations have signed.
On the surface, it's a behavioral framework for peaceful exploration.
Transparency, sharing scientific data, emergency assistance for astronauts.
But strategically, it's about setting the rules before someone else does, right?
Exactly. Establishing Western democratic norms as the default operational baseline in space.
Getting emerging space powers like India and Brazil to sign build a massive interoperable coalition.
Because there is a rival coalition, there's a distinct bifurcation in space right now.
The source material notes the Wolf Amendment. What is that?
Passed in 2011, it legally prohibits NASA from engaging in any direct bilateral cooperation with the Chinese government or its space agency.
Citing espionage and human rights concerns. So NASA literally cannot coordinate a mission with China without breaking federal law.
Correct. So you have the U.S.-led Artemis coalition, and you have China forming its own lunar research project, partnering with Russia.
Two competing blocs heading for the exact same resources at the lunar South Pole.
Operating under entirely different legal frameworks.
Yet, despite extreme tensions on Earth, NASA and Russian cosmonauts are still flying on each other's rockets to the ISS.
Space has an incredible capacity to act as a diplomatic pressure valve. Physics demands cooperation in orbit.
But as we establish permanent infrastructure on the moon, the logistics require cooperation that literally breaks the laws of physics as we know them, which brings us to coordinated lunar time.
In 2024, the U.S. government tasked NASA with establishing a standardized time system for the moon, expected to be formalized this year in 2026.
Explain this to me like I'm 5, because they aren't just setting up a new time zone. Time literally moves at a different speed on the moon.
It is the reality of Einstein's relativity. Gravity warps the fabric of space-time. The Earth has more mass, so a stronger gravitational field.
And the moon has less gravity.
So time moves slightly faster there relative to a clock on Earth, specifically 58.7 microseconds faster every single day.
Okay, so imagine two runners. The Earth runner is running through deep mud, that's our heavy gravity dragging on time.
And the moon runner is on a clean track, ticking ahead slightly faster.
But we're only talking about 58 microseconds a day. Why does that matter?
Because in modern navigation, time's distance, light travels at roughly 1 foot per nanosecond.
Okay.
If you're building a global lunar GPS network to coordinate spacecraft from multiple nations, a microsecond discrepancy translates into massive navigational errors.
If your clock is off by 58 microseconds, your computer thinks you are miles away from where you actually are.
You will crash into the side of a crater.
So you have to establish a unified mathematical standard that accounts for relativity.
And strategically, establishing coordinated lunar time is like establishing the Greenwich Meridian in the 19th century.
He who sets the clock sets the rules.
It's the ultimate assertion of infrastructure. By defining how time itself is measured, NASA and its partners are laying the foundational architecture for human civilization off-world.
It proves lunar exploration has matured from temporary camping trips into permanent industrialization.
Exactly.
So we've unpacked the whole timeline. NASA started in a World War I aviation lag, born out of Cold War panic.
Sprinted to the moon by brute forcing the engineering.
Built an orbital laboratory over 30 years, surviving disasters. Disrupted its own bureaucracy by shifting to a venture capitalist commercial model.
And now, funding private space stations, deflecting asteroids, pushing nuclear propulsion, and writing the rules for time on the moon.
And all that serves a larger purpose. Every time you check a weather app or marvel at an infrared image from JWST,
you're seeing the direct, tangible results of an agency tasked with pushing the absolute boundaries of what is possible.
But as we wrap up, I want to leave you with a final thought to mull over. NASA is fundamentally changing. contracting private companies, building nuclear-powered lunar bases to secure keep-out zones.
We are entering an entirely new era.
At what point does NASA have to transition from being an agency of pure exploration to becoming the regulator, the governor, and the traffic cop of a highly populated, industrialized solar system?
If massive corporations own the ships and competing nations are staking out territory, who enforces the speed limits and property lines in deep space?
It's something to think about the next time you look up at the moon.
Thank you for joining us on this deep dive into the source material.
We'll see you next time.